Hi, I'm Austin. I'm going to be talking about the steady state solution to forced vibration problems. First, we're going to start with the general form of the differential equation for a forced vibration problem. The forcing function is given by f naught cosine omega t over m. The total solution is given by x of s is equal to the steady state solution plus the transient solution. Through some derivation, we get that the steady state solution is equal to this equation. Phi right here is the phase angle and is given by this equation right here. And this part of the steady state solution, SGN of omega n minus omega, simply gives a positive or negative value to the entire thing. The denominator of this equation is the amplification factor. And the amplification factor can be thought of as a ratio of the steady state's amplitude to the static deflection amplitude. The static deflection amplitude is achieved by setting omega equal to 0 and then solving for the steady state solution.
How's it going, guys? My name is Sam, and I'm going to be talking about the complete solution. And this is for the undue damped case. So picking up where Austin left off, we have our transient response and our steady state response. This gives us this big lengthy equation. So in order to find both our C1 and our C2, we're going to do a similar process to what we've done in kind of our past problems and homeworks. So we'll take initial conditions and differentiate the original equation. So we get this very elongated expression that I'm sure we are all going to enjoy doing in our homeworks. And then we'll take C1 and C2, and this is what these eventually equal. And then so there we can manipulate the equation and start using it. And if you miss any of that, you can find it in page 31 and 32 of your script.
So in class we learned about the resonant frequency. So that's the frequency at which the forcing function can really drive up our steady state displacement. And that is equal to this equation up here. And we find that by setting the derivative of the amplification factor equal to 0. When we find this resonant frequency, we're also able to find the max amplitude, peak amplitude of the amplification factor. And that's just by plugging in this value into the amplification factor equation. So that's pretty neat. And it's also worth noting that our forcing function and steady state displacement are also out of phase. In other words, this steady state displacement lags the forcing function by a value of t equal to negative phi over omega.
Hey guys, my name is Aaron Afriat, and today I'm going to talk about a special case where the amplification factor equals to infinity. And that's when you have a forced vibration at a damping ratio equals 0 at natural frequency. And the approach when you encounter that problem is to plug in the damping ratio equals 0 and omega equals omega n to equation 2.90 in our text, which will give you this equation. And then you have to guess a steady state solution of b times t times cosine of omega and t plus phi. And then we'll go here. We are going to take the derivative of the steady state solution twice and plug all the three equations into 2.90, which will give us this equation. And our goal here is basically to find the coefficient b. And so the shortcut is to set sine of omega and t plus phi equals cosine of omega and t at t equals 0, which will give us a phase angle of pi over 2 and will allow us to solve for b, which equals negative f naught over 2 times omega times m, which you can plug that back into the steady state solution and find the full steady state solution with this equation.